So why do we care about ultraviolet spectroscopy when we're talking about the particle in a box model, or even so simply as the particle on a line model, because we're only in one dimension so far? So we care because actually we can think about linear conjugated organic molecules as being sort of like a particle on a line, or particles on a line. So why is that? Let's take 1,3-butadiene as an example. So I've got this drawn both in organic shorthand, which only draws the bonds between carbons or heavy atoms, so it excludes all hydrogens, as well as drawn out with all the hydrogens written explicitly. So we have a carbon with 3 hydrogens double bonded to a carbon with 2 hydrogens, single bonded to another carbon with 2 hydrogens, double bonded to yet another carbon with 3 hydrogens. So we have 2 double bonds separated by 1 single bond if we think just about the carbon backbone of this molecule. And so when we have alternating single and double bonds between carbon atoms in, say, a hydrocarbon molecule, this is known as conjugation. So this is a conjugated hydrocarbon. And the path drawn in red here along this conjugated segment, or double bond, single bond, and we could go on and on forever, we can think of that as being like an electron highway, where the pi electrons, so only the electrons involved in the double bonds, the pi electrons are really free to move along that entire length of the molecule. And so if we were to draw this as a straight line, we're really saying carbon, double bond, carbon, single bond, carbon, double bond, carbon. That's the length of our line. So we're thinking about particle on a line, particle in a box in one dimension. That would be the box length, A. So can we calculate that? Well, so we could look up what the average value for a carbon-carbon single bond is. It turns out to be 1.54 angstroms. A carbon-carbon double bond has an average bond length of 1.34 angstroms, and a carbon has an atomic radius on average of 70 picometers, or 0.70 angstroms. So what is the length of this? So we have a carbon radius on each end, and then we really have 2 carbon-carbon double bonds and 1 carbon-carbon single bond. The radius on the end points is because half of that carbon on either end is involved in a bond, but the other half is just the radius of the atom. So we have to account for sort of that other half of the atom, especially since we're ignoring all of our hydrogens. So we could calculate the length of our line here, or A, as 2 times the value of the carbon radius, atomic radius, which is 0.7 angstroms, plus 2 times 1.34 angstroms, which is our average carbon-carbon double bond length, plus 1.54 angstroms, which is our average carbon-carbon single bond length. And we should get 5.62 angstroms for the length of this electron pathway, or the length of our box. And so how many electrons can traverse this highway or this box in theory? How many pi electrons does 1,3-butadiene have? So it's going to have 2 for each double bond. So it's going to have 4 total pi electrons. And we could think of drawing our energy diagram for a particle on a line, or a one-dimensional particle in a box. There's no degeneracy yet. If you don't know what that word means, that's okay. We're going to talk about it on another day. But we have 2 electrons that can fit in each energy level, or each state, or each orbital, right? All of these words are going to sort of become synonymous within the context of this course. So just like we could pair electrons in general chemistry, we can pair electrons here. So and just like in general chemistry, we're going to use that off-bow principle and start at the lowest energy and fill up. So let's put our 4 electrons into this energy diagram. We'll see that we have 2 electrons in n equals 1, 2 electrons in n equals 2, and so our ground state would be our n equals 2, and we could think about taking one of those electrons and using light to excite it up to n equals 3. So our transition here might be from n equals 2 to n equals 3 if we're absorbing a photon as this molecule. And so we could think about figuring out what wavelength that should happen at by taking the energy, and here we'll use the equation for a particle in a box, a one-dimensional box, when n equals 3, minus the energy when n equals 2 for the same system, and that's going to give us the transition energy, or the difference in energy between those two possible states. And then, of course, energy is related to wavelength through Planck's constant times the speed of light divided by wavelength. And with UV-Vis spectroscopy, we are able to measure the wavelength at which light gets absorbed. So this should correspond to the wavelength that we can measure. We're going to be exploring this in our Particle in a Box lab, particularly on Thursday. Thursday's part of the lab, we're going to be exploring this with bigger, crazier molecules than cute little 1,3-butadiene, but we will be practicing this a little bit in class as well. So this is why we might use, or when we might use, a simple system such as a one-dimensional particle in a box, which obviously is not a real system, but it is a model system that can sometimes be useful.